So dear students, previously we have learned the motion of a charged particle placed in a uniform magnetic field. But today we will see the motion of a charged particle when placed in a uniform electric field. So for that we need an electric field. So in the diagram you can see that is the x and the y axis. So two plates have been taken. The positively charged plate is placed in the below, and in the above negatively charged particle and negatively charged plate is placed. So it means the lower plate is positively charged and the upper plate is negatively charged. So obviously an electric field has been created, and since the lower plate is positively charged and upper plate is negatively charged, so it is very clear that the electric field will act from lower plate to upper plate. It means the direction of the electric field is from positive plate to negative plate, that is from x axis to y axis. I think it is clear, because electric field always acts from positive charge to negative charge, just like magnetic field, as it acts from north pole to south pole outside the magnet. So the electric field acts from positive charge to negative charge, that is from positive plate to negative plate, that is in the upward direction. Now suppose a positively charged particle, a point charge of having charge plus q of mass v, is moving inside this electric field with velocity v. Plus q charge having mass m with velocity v is just thrown, or it is just entered into this electric field in x axis. Okay, since this is x axis and this is y axis, so it is just moving, it just get and make an entry into this electric field along x axis. Clear? So we all know that is, since the electric field is created, so obviously due to this electric field, the electric field is always known that F is equal to Q. This is the magnitude of the electric field. Clear? But since the electric field is acting, from x axis to y axis in the upward direction, and the charged particle is moving in this electric field along x axis, so it will experience no force along x axis. Clear? Why? Because electric field is acting in the upward direction and it is moving in the xy, in the x axis towards the x axis, along x axis. So its x component force is 0, but it will have a component of force along y axis. It means along y axis it will experience a force, that is QV. Clear? As I said, since electric field is acting in the upward direction along y axis. Very clear. There should be no confusion with this. Now, so since there is force acting on this, so obviously it will experience some acceleration. Now since force acting along x-axis on this particle is 0, so obviously there will be no acceleration along x-axis. So that's why a suffix x indicates its acceleration along y-axis is 0, having no acceleration along x-axis. But since the charged particle experiences a force along y-axis, so obviously it will have an acceleration. We all know that F is equal to ma, so A is equal to F by m dividing by mass. This is the value of the component of acceleration along y-axis. Now since the particle has no acceleration means when it moves with a constant velocity. Velocity is not changing, so it will still move with velocity along x-axis. Constant velocity means no change in velocity, that's why acceleration is 0. So since it keeps moving with velocity v along x-axis, so the distance traveled by this charged particle along x-axis in time t is x equals to vt. Clear? Similarly, the distance along y-axis traveled by the particle is y is equal to vt plus half at square, using the equation s is equal to ut plus half at square. Now since the particle has no initial velocity along y-axis, why? Just remember, the particle just entered into this electric field along x-axis because it had no initial velocity along y-axis? Because it didn't start its motion along y-axis. Since it started its motion along x-axis. So that's why it had initial velocity along x-axis, but its initial velocity is 0. But after entering this electric field, it then experiences an acceleration. So initial velocity is 0, half a t square. A represents the acceleration along y-axis, half a t square. So now we will put the value of both ay and time t. So half a t square, value of a is equal to qe by m, then t is equal to x equals to vt, so t is equal to x by v square. So calculating, we get qe by twice mv square into x square. It is exactly the equation of y is equal to ax square. This is the standard equation of a parabola. Clear? So that's why, since it is the equation of a parabola, so it will follow the path of the parabola. So that's why you can see it will just take off like an aeroplane, and it will just move in the upward direction. So that's why it will just, after entering this electric field, it will experience a force and it will just trajectory. It is just like the trajectory in the above direction. Now it is, one concept is very clear, that since the particle is positively charged, so obviously, and the upper plate is negatively charged, so according to theory you can clearly understand by this that we all know that opposite charges attracts, so the charge will be, this is one simple concept. So that's why it is experiences a force along negative axis, that is along negative charge, because the particle is positively charged. So that's why it experiences a force along negatively, it is attracted by the negative plate, unlike charges. So that's why it is moving, it is along y-axis and taking a parabolic path. If the charge contains, if the charge was a negative particle, negatively charged, then it would experience a force along positively charged particle. Clear? Obviously. So you can see, so that's why now after leaving this electric field, it will just keep continuing in the upward direction with the final velocity, that is the velocity it grab after leaving this electric field. Clear? And it will just keep along. Okay. So this is the motion of a charged particle in a uniform electric field. Very easy. Moves on to what will happen if a charged particle is placed, okay, in an electromagnetic field. It means a field where both electric and magnetic field is present. Just like light, we all know that light is an electromagnetic wave. So just like that, which is also called Lorentz force. So let's see. Now suppose you can see the diagram here, and an electric charge. Okay, now first of all, we will see that at first we have drawn a three-dimensional space. Okay, so here electric field, E represents electric field. Here electric field is acting along x-axis. Clear? Magnetic field B is acting along y-axis, and the charge is moving with velocity v along z-axis. So these three axes are mutually perpendicular to each other. Very easy. So now, since it contains both electric and magnetic field, so according to electric field, so the charge will experience an electric force. We all know that F is equal to QE, it denotes electric field. So F is equal to QE. Now due to magnetic field, it will also experience a magnetic force. So that's why Fm, that is magnetic force, F is equal to Q into V cross B. We have already learned. Okay. So total electromagnetic force, EM force means electromagnetic force. It is called Lorentz force also. So FL, L indicates Lorentz. So this plus this, that is F electric field, electric force plus magnetic force. That is QE plus Q into V cross B. Taking Q common outside, Q into E plus V cross B. Now, what will be the direction? This electric force is acting here. Magnetic field is here. So what will be the direction of the magnetic force acting on this point charge? For that, we will use Fleming's left hand. That is the motor rule. We can easily find out the direction of the magnetic force acting on the particle. Now if we place, now since this is the magnetic field, we will use Fleming's left hand rule. So you can see the index is towards the magnetic field. Clear? I have to twist the hand. Okay, so much. This is the velocity of the charged particle, which is nothing but the current, because we all know that moving charge means current means moving charge. So if we, this is the direction of the magnetic field, index finger, middle finger indicates the direction of the charged particle. So you can see the thumb, left thumb will indicate the direction of the magnetic force. This is not this, this is, if we place, you may say like this, no, you can see it is not perpendicular, this is like this. Clear? Magnetic field, motion of the charged particle or current, that is the force. It means it will act. This is the direction of the, clear? Clear? You can see this is not in this direction, this is in the negative x-axis. So the magnetic force, the direction of the magnetic force will be just opposite to the direction of the electric force, isn't it? Opposite. So now, if electric and magnetic field both are perpendicular to each other, clear? And the direction of both electric and magnetic forces are opposite in direction, but if we keep their magnitude equal, one thing, if we adjust by adjusting their direction, and if we equalize their value, what we will get? Then in that case, if both are equal and opposite, then it will be 0 QV minus QVB. If both are equal, that is FE and that is FM. So if they are opposite and equal to each other, so it will just cancel each other, isn't it? Just like if it is, it means it is Fe minus Fm. Clear? Q is equal to Fe and Q into V cross B is Fm. Now if their magnitude is equal, if they are equal, then it will be 0. Very clear? So in that case, it means the total Lorentz force acting on that particle will be 0. It means it will experience no force. Then what will be the result? Now since it will experience no force, so it will just keep moving. It will just keep maintaining its initial velocity. Without any deflection, it will not be deflected to any side. Without, it will just maintain its velocity around this. So under such condition, we can say, it means if both electric and magnetic field are perpendicular to each other, if both the forces are opposite in direction, but if we equalize their magnitude is same, then we can say Q equals to QVB. It means in that case, the electric force is equal to magnetic force and then velocity is equal to E by B. It means the velocity will be the ratio of electric field by magnetic field, both perpendicular to each other. Perfect example is light. Light is such an electromagnetic wave, all electromagnetic wave. Both electric and magnetic field are perpendicular to each other, and then it vibrates, or this wave travels in a direction perpendicular to both electric and magnetic field. Clear? So this is Lorentz force, means total force acting on a charged particle both due to electric field and magnetic field. If these two fields are perpendicular to each other and forces are opposite to each other, and if their magnitude is same, then the velocity will be the ratio of both electric field and magnetic field, not magnetic field to electric field by magnetic field, and it will just keep moving in a straight line.